Hello everyone. Let's talk about arc length of a vector function, r of t. Let's restrict this vector function to 2D just so it makes sense here. So we have some vector function where there's an x component and there's a y component. And we're asked, why do we re-parameterize this vector function? So let's go through that now. So let's say we want to find a function that expresses the arc length of this specific vector function. So what we would do is we'd find the derivative of the vector functions. We'd do r prime of t, and we'd say that that is equal to f prime of t I plus g prime of t, and we add that k variable on. Okay, and we know that we now have to take the magnitude of the first derivative vector function. So it looks something like this, right? And we take the square root, f prime of t squared plus g prime of t. And we'll square that too. So we know that the overall arc length, which we'll call s of t, being the function that gives us this vector function, is equal to the integral from point A to point B, or in this case, from wherever we start our vector function, so some domain, and then to point t. So it's a little weird to use this t variable here since we have a function of t and then we're plugging in t, right? So we just give it a dummy variable, which we'll call u. So let's just call this s of u. So s of u is still equal to this, and that's going to be the magnitude of r prime, and instead of t, let's just call this u. So r prime of u, kind of like just a dummy variable. And let's integrate this with respect to du. So why exactly do we do this here? Well, there's a few reasons. If we were to just not integrate this with these upper and lower limits, well, we'd have a plus c, and for arc length, that doesn't make much sense. So doing this method negates that fact, right? So A is where we start, T is where we end. It's still the same thing as taking a indefinite integral, but defining it definitely, and therefore you get still arc length of the overall function, just in a different way. Okay, it also negates some of the domain restrictions. If we were to just do a solid integral without t or a present, well, let's say the function's domain, right? So if we just took the integral of this, right, and then we did it with respect to t, right, there's no restrictions on the integration domain. So when we do this, right, let's say our function's domain is defined, let's say it's only from defined at 0 and goes to infinity, right? So all real positive numbers, right? Not negative numbers. That might arise at like a, let me just see here, maybe like ln of a negative number. I can't really think of anything else off the top of my head, but let's say you have that domain restriction. Well, if the domain is restricted in your arc length, if you were to take the integral of this, right, we would say, okay, this is, let's call this s of t, right? What we're trying to get the function for the arc length that we can plug in t and get an arc length, right? That just doesn't work, okay? Because if we let's say time negative, right? You're basically saying that the domain is all real numbers. So like, let's say T is a set of very bad at drawing the R, but that's what I'll draw. So those are the two reasons we really do reparameterization. Mainly the first one I talked about, right? We want to make sure that the domain works. And also we negate plus C because there is no real plus C in an arc length bound within a definite integral. So, or sorry, an indefinite integral. So hopefully you enjoyed. If you did, drop a like, comment, subscribe. I'd appreciate it. Have a wonderful day. Bye-bye.